Thank you. Yes, actually, this work is a part of the master thesis of Habib, but he couldn't attend here, so I will present. I supervise this thesis work. So the presentation deals with the derivation of state-dependent fragility curves. Clearly, we have already seen that in previous presentations. Traditional fragility models assume that buildings are actually undamaged when seismic events happen. While state-dependent fragility curves consider that buildings could have a certain damage level when a seismic event happens. And so they give us the probability of exceeding a certain damage state given not only the intensity of the ground motion, but also given existing damage level. So the objective of this work were basically defining a procedure for deriving state-dependent fragility curves using cloud analysis, with specific focus on the regression models that can be used to this scope in order to avoid a common problem in fragility models, which is the obtaining fragility curves that overlap, as you see in the right, in the right plot. Since fragility curves give the probability of exceeding a certain damage level, of course, we cannot have, as you see in the figure, that the probability for exceeding damage 1, for instance, at some point becomes lower than the probability of exceeding damage 2, because this wouldn't make sense for an exceeding probability. So this was the main focus of the work. So the procedure is actually based on cloud analysis. So you all know very well that in cloud analysis we take typically a large number of unscaled recorded ground motions with a wide range of values of the intensity measure. We apply them to, say, numerical models. We perform nonlinear dynamic analysis, and then we use some form of regression models to derive fragility curves. So what are the models that we considered as a case study? And then I will mainly focus on the regression models. The models that we studied were basically taken from the literature, in particular from Orlacchio and others. So they are equivalent single degree of freedom models that these authors defined in order to represent the behavior of different in-field frames. So as you can see from the slide, there are three different groups of models that represent different levels of seismic design. And for each group, we have a different number of stories. So then, for each of these case study structure, the behavior is represented through a certain backbone curve that, as I mentioned before, we took from the literature. So this is an example of the backbone curves that we used for the different models. Now, the procedures that we studied are actually valid, independently from the model, but we decided to use this as an exercise. As for the definition of the damage model, we again followed what was already done in the literature. So we have the levels that you see there. So we have no damage, which is damage 0, and then we have 4 increasing levels of damage from 1 to 4, and they are based on the maximum displacement during that is measured during the nonlinear dynamic analysis. So the engineering demand parameter is the maximum absolute value of the displacement. The thresholds of damage are deterministic in this case, and they are defined as a function of the key points of the backbone curve. Again, we follow the literature on this as well. The backbone models are also associated to hysteretic degradation models, which are, say, implemented through the pinching for OpenSys model. So at the end of the day, we have, say, a backbone curve that also have degradation through the different cycles. As for the ground motion intensity measures, we considered different, say, average spectral accelerations, so which are those that you see here. So for each ground motion, we computed the average spectral acceleration in the intervals that you see in the slide, so between 0 and 0.5 seconds, 0.3, 0.6, and so on. And for each of the case study structures, we actually used the ground motion intensity measure that had the largest efficiency. I will go back to that in a few slides. We also considered two different ways of computing these average values, either the geometric mean that has some advantages when we have to combine that with hazard, or the arithmetic mean. But now this is a detail which is probably not so important. So what is the procedure that we used? So we started with a large number of ground motion records, which is 1,382. And we apply all of them to each of the models. So this is a, say, standard cloud analysis. Then, once we have the results of this analysis, we can classify the results and assign damage to each of the say, analysis outcomes. Now, this first set of data is what we can use in order to calibrate the fragility models for damage state 0, so undamaged structure. Then, we can take each of those results and run another analysis with each of the ground motions to obtain data to fit state-dependent fragility models for structures that have already some damage. So, for instance, if we take all the models that have an initial damage, now there is a mistake here in the arrow, for some reason they should be shifted down. If we take all the models with initial damage DS1, so they should point here, we can take all those models and run again the analysis with the same ground motions. And so we'll obtain, say, the same number of results again, but now we have structures that do not start from the undamaged condition, but with a certain initial condition. Then we can do the same for all the others. So each model basically goes through two different analyses, starting from the undamaged state, and then it's classified. So, as I mentioned before, to define the engineering demand, the intensity measure to be used, we checked the efficiency, and to check the efficiency, we used we basically evaluated the scatter in the maximum displacement values in the initial analysis that we perform with the structure in the undamaged state. To do that, we also normalized the values of the intensity measure to transform that into a standard normal variable. So what are the regression models that we can then use in order to fit the fragility models? The main focus here was on probit-based regression. So the most simple regression model that we can clearly use is a standard probit. So in standard probit, we basically say that the probability of exceeding a certain damage state is written as a standard cumulative normal function based on the logarithm of the IM. Of course, if we fit this type of model on each groups of data, so if independently, we will have no guarantee that the different curves will not overlap. So we could obtain something like this, in which, for instance, the probability of exceeding damage state 3 and 4, given damage 0, at some point will cross each other, which again is not possible from the logical point of view. This can also be easily visualized considering the linear predictor, which is basically the inverse of the normal cumulative distribution function of the function that is written at the top of the slide. So when we have this overlapping, it means that in the linear predictor we'll see two lines that cross each other. So clearly the easiest solution that we have to avoid overlapping is to use ordinal probit. Ordinal probit is, say, a class of statistical models that, say, maintains order between, say, the observed variables. So in this case, damage becomes an integer variable that can go from 0 to 4, and the model will maintain the order. To visualize the model, it's very easy to use the linear predictor, because, again, the linear predictor is, again, feed to the -1 of the exceedance probability. In this case, the most simple ordinal probit model basically associate to each the probability of exceeding each damage level a straight line, and all the lines associated to different damage levels must be parallel in order to avoid overlapping. So clearly, a standard ordinal model will guarantee that curves starting from the same damage level will not overlap, but it will not guarantee that curves for exceeding a certain damage level starting from different initial damages will not overlap, as you see on the right. Of course, this from the logical point of view could happen, but probably I would say that engineering judgment may suggest that the probability of exceeding damage should increase if we start from an higher initial damage, even if, again, from the logical point of view, it could happen. So, because of that, we also investigated models that will not allow any overlapping of fragility curves, neither when we start from the same initial damage, nor when we consider exceeding probability of different damage levels starting from different initial damage values. So we proposed a model that we called conditional probability. Now this is maybe, from the mathematical point of view, this is not the most, elegant solution, but in this model what we do is, and we can easily visualize that from the linear predictor that you see on the left. In this case, we define an interval of intensity measure values, and we want to have that within that interval, that can be as wide as we like, the fragility curves will not overlap. So the boundaries of this interval are indicated as the logarithm of L and the logarithm of U. And basically, when we fit this model, we introduce a number of constraints such that the lines associated to the probabilities of exceeding the different damage levels will never cross each other within the interval of interest. In this model, based on how it is defined, the calibration of the different fragility curves is carried out in a sequence. So we first calibrate the fragility models and the parameters for the probability of exceedance of the damage 1 given no initial damage, and then we move towards higher damage values. And then, whenever we do that, we force, with some proper constraints, that the curves will not cross each other. Of course, this could have some issues related to the fact that since we start by fitting the initial, lower damage level first, in the definition of the slopes of the fragility curves, those models will have somehow a priority in the calibration of the model. So because of that, we also define another model that is called ordinal probability on combined dataset with average slope. So this is an ordinal probability in which we have two ordinal parameters, one ordinal parameter that is gamma 0I that is associated to the initial damage, and another ordinal parameter that is associated to the damage state that we are considering as the exceedance damage state. And so in this case we fit all the data set at the same time, and we calibrate these gamma 0I and gamma 1j parameters as well as the slope parameter, which is the same for all the damage levels in this case. Calibration is carried out using, maximum likelihood. You can see the likelihood function in the slide, but now there is no time to get into the details. So in this case, we basically obtain, in terms of linear predictor, a number of parallel curves, but we also force that not only curves starting from the same damage level will not cross each other, but also curves that give the exceedance probability of a certain damage starting from different initial damages will not cross each other. And finally, we have also the ordinal probability with different slopes. This is similar to the previous one, but in this case, the slope, beta, the beta parameter, changes depending on the damage state. Again, this cannot be done for any value of the intensity measure because it's physically, mathematically impossible, but otherwise we would go back to the previous model. We fix a range in which we want to avoid this crossing. So as to give you an example of the results, we see here a calibration, for instance, of the probability of exceedance of damage state 3 given damage state 0, 1, and 2, and as you can see in this case, which are calibrated using standard probability, we can have some overlapping of the curves that we want to avoid. And with all the other models that we investigated, of course, this will not happen. Now I think I'm running out of time. So just to summarize, then we also performed some, say, different analysis of the results, because the case studies were many, and I mean, but now there is no time to present everything. So in general, when we use the standard probability model for low initial damage states, we don't have a lot of issues in terms of crossing of the curves, but the overlapping problem mainly emerges for higher damage states, where the number of data points is clearly more limited. So standard ordinal models addresses the overlapping issue when evaluating fragility across damage states for a given initial condition, but it fails to maintain the order when we start from different initial damage conditions. So to overcome that, we can use the models on combined data sets. So, and something else that we did was comparing these models to, because of course when we introduce these more complex models, we are somehow introducing constraints to the models themselves. So they may not be able to describe data very well, because they may not have enough degrees of freedom. So we also compare them with standard probability models, which are somehow the models that give the, say, most degrees of freedom in the calibration, and we compare the error, and we found that the errors, the models that have the least error are basically the conditional probability and the ordinal probability with combined data sets with different slopes, because of course they are the models that have the largest degrees of freedom. So in conclusion, we investigated different regression models that are within the family of, say, probit models to calibrate state-dependent fragility curves in order to avoid overlapping between curves. We found that the most suitable models are conditional, what we called conditional probability and ordinal probability with, say, different slopes, and some, say, possible, say, future developments are, of course, using more, say, advanced structural models. Of course, now it was not the scope of the work here, and also maybe investigate the use of different intensity measures for structures that start from different damage states, because we can expect that since there is a period elongation after damage, maybe the most efficient damage measure, intensity measure will not be the same as damage increases in structure. So thank you very much for your attention.